Well, thank you very much, Chris. Can everyone hear me at the back there? Cool. Well, while I'm the person up here talking and delivering all this work, I should emphasise from the very beginning that I'm just the section leader. I don't do most of the work. Most of the work is done by the people on this screen, particularly people from my section, the Earthquake Hazard section, like Mark Leonard, Trevor Allen, Dan Clark, Andrew McPherson, and so on, and also from the Risk Analysis Methods section. And I should also acknowledge the work done by corporate and IT to get all the IT systems up and working, which allowed us to do this map. Now, basically, this talk is going to be divided into 6 chapters. The first chapter is more of a general introduction to earthquakes in Australia for the benefit of those who aren't familiar with the field. The next 4 chapters basically cover different aspects of earthquake seismology which we use to produce the earthquake hazard map, which I'll talk about in chapter 6. So first off, we'll start with chapter 1. Now, for those who don't know, Australia does get earthquakes, which is just as well for this talk, otherwise it would be very short. This is a map produced by Lauren Power and others in the vulnerability section a few years ago, and it shows the distribution of earthquakes from 1788 to 2008 as blue dots, ranging in size from magnitude 4 to about a magnitude 7 on this particular scale. And the background image shows the building structural value from Nexus, the Geoscience Australia's exposure database, for residential structures expressed as dollars per square metre. So the light brown areas indicate basically there's not much there, while the darker colours and the red colours indicate a large amount of exposure. So the first point you notice that there's some big blue dots on this map. Second point, you notice that a lot of those big blue dots are in the light brown areas where there isn't actually a lot exposed. Now I'm going to talk about several sequences of earthquakes repeatedly through this talk, so I thought I'd identify them straight up. This is the Tennant Creek sequence. You're going to hear a lot about that. It's an example of a big earthquake in an area without much exposure apart from a gas pipeline, indicated by the dotted line here. Mickering, which is one of these earthquakes in this area, which is an example of a big earthquake in a low exposure area, but not zero. And the Newcastle earthquake, which is an example of a moderate earthquake in a high exposure area. So this is what happened in Tennant Creek in 1988. Basically there is a sequence of 3 magnitude 6 plus earthquakes within the space of 12 hours, each one triggering the next one. To give you some idea of scale, that's about the same as the Christchurch earthquake, give or take a bit, which killed 188 people, but out in the middle of nowhere it basically just bent a pipeline, shown in the bottom left hand corner. And estimated costs somewhere in the vicinity of a few $1 million. Meckering, about the same size as the largest of the Tennant earthquakes, but only one of them. It occurred in an area with greater exposure, caused about 20 times as much damage, about 57 million. And it also created what's called a fault scarp. A fault scarp occurs when you get a very big earthquake close to the surface, and it pushes up the surface by, in this case, several metres. And you can see from the scale, the figure on the top there, that this was a huge feature, 40 kilometres long, several metres high, higher than a jeep. But it occurred in the middle of a wheat field rather than the middle of a city. Here's an example of a much smaller earthquake, magnitude 5.7, Newcastle. Now, magnitude is a logarithmic scale, so this released about 30 times less energy, but it occurred in a populated area, and according to the EMA disaster database, in modern terms that would have been a $3 billion disaster, killed 13 people. Yet it was a much smaller earthquake. So you can see about for earthquakes in terms of impact, it's all about location, location, location. And we've been lucky, really, that Newcastle was the largest earthquake we've had in a populated area within the last few hundred years. If we had a 6.7 in a populated area, no one would ask the question whether earthquakes occur within Australia. So who wants to forecast it? Who wants to know the likelihood of these things? Obviously we do. Chris does. He gave me the job of doing it. But outside of GA, who wants to know? The main user of this kind of product that we produce are engineers for designing their buildings. They like to know how much shaking they need to incorporate in their design through the building code usually. Other than them, emergency managers obviously would like to know how much shaking they need to consider in their planning and preparation for a natural disaster, particularly an earthquake. A lot of our information is also used by reinsurers. Reinsurers are the people who give insurance companies insurance, and they would like to know how much to basically cost their policies. And we've been told informally that a big earthquake in Sydney is one of the biggest risks they have globally, in fact. All 3 are basically interested in the same kind of thing. They're interested in the likelihood of an earthquake within the next 50 to 100 years, which is a typical lifespan of a sort of building in Australia. Not all buildings, but most buildings. So that sort of time frame is really going to influence and control how we're going to put together the hazmat. We're interested in the likelihood of an earthquake over the next 50 years or so. But earthquakes are unpredictable. This has been in the news quite a lot lately. We can't predict when, where, or how. So this presents us with a problem. How do we forecast the likelihood of something which is unpredictable? And expressing it this way, it looks like a job for him rather than me. This is Tom Cruise, Mission Impossible. And like Tom, we sometimes have to hang a lot of weight from a very thin line of evidence. However, the mission is not in fact impossible. He did pull this off. And hopefully by the end of this talk we'll convince you that we can also pull it off. Now what we don't do is prediction. We don't predict when, where and how big an earthquake will be. What we do is forecast. We look at the likelihood of a certain size event over a period of time. It's like the difference between predicting that there will be rain tomorrow and predicting that there was a 70% chance of rain tomorrow. We do the latter. We do forecasting. And there's a fundamental concept in geology which I'm going to sort of twist a little bit for earthquake hazard. There's a statement most geologists know: the present is the key to the past. This idea was originally put forward by James Hutton, and that phrase, according to Wikipedia, was originally put in that way by Charles Lyell. And the idea here is basically, by looking at the geology you see around you at the moment, you get an idea of what happened in the past, how it got there, how the fossils ended up on the top of the mountain range. For us, the past, we're interested in the past, but we're interested in the past as the key to the future. Our focus is trying to look at what will happen, as Chris said, in this case over the next 50 years. We're still interested in the past, but we're interested in the past as a guide to what might happen in the future. And it's a limited guide, but it is a guide. So first of all, what I'm going to talk about is a little bit about the Australian Earthquake Catalogue, which is basically just a list of longs, magnitudes and times of earthquakes in Australia. This project's been going on for as long as I've been at GA, and it still continues. The main problem is that earthquakes have been going on in Australia longer than any particular agency or seismic network has existed. From basically 1788 is the first recorded instance of an earthquake in Australia since European settlement. Also, higher density networks, meaning networks with seismometers closer together, can detect smaller earthquakes than low density networks like the national network. That means to get a complete picture, we need to combine catalogues from different networks, from the national network and from local or regional networks, in order to get a better picture of the history of seismicity in Australia. This is what we're currently up to. This is just a big list to show you. I don't expect you to read it all. There's about 60 different names here. There's about 40 different organisations. They range from Geoscience Australia to state-based agencies which do regional earthquake locations, to universities which at some stages used to run their own seismic networks, to individuals, to private sector companies. So we have a much more comprehensive catalogue, but it's much more heterogeneous. There's a huge array of different authors here. And as anyone in this agency knows, combining data sets from heterogeneous organisations is a challenge, and there's a challenge usually because of the lack of metadata surrounding exactly what they mean by various terms. I'll talk about one example which caused us the most grief for this particular project, and that is the definition of this tricky word called magnitude. What is earthquake magnitude? Well, I'll just give you one example. This is what's called the local magnitude. It's sometimes called the Richter scale. It's the one you hear about in the news all the time. It's the log of the maximum amplitude of a seismic wave at a seismic station A minus the log of a function A naught of delta, which depends on distance. And basically the further you're away from the earthquake, the smaller the amplitude of the earthquake, and you need to take that into consideration when you're calculating the magnitude. Now this would all be fine if A naught was the same everywhere in the world, but it isn't. There was the original one developed by Richter for California, and really there should be different functions of A naught for different parts of Australia, for different parts of the world. This presents us with a difficulty because, generally speaking, not everyone actually tells you which version they were using at which particular time for just local magnitude. So this is a graph produced by Trevor Allen. It shows the difference between the correction of the traditional Richter scale and what was used by 4 different agencies in different times in Australia, indicated by the curves, and I'm showing it as a function of the distance. For the red, blue and green curves, but around 100 kilometres, all these different formulas give you about the same value. But if your station's 500 kilometres away, they differ by up to half a magnitude units, and this is because the models which are underlying this are different. There's different amounts of attenuation in different parts of Australia. And if you don't know which function was used, you can't really compare them. It's an apples to oranges comparison. So we had to go through the process of trying to work out who was using what formula when and try to correct them all to a consistent magnitude scale. And that was one of Trevor Allen's main jobs for the last few years. And he ended up with this. So this is actually correcting some of the older earthquakes to a modern scale, which we think is the most accurate scale for that area based on what we can know at the moment. Each earthquake here is coloured red if it went down, compared to what it used to be, and blue if it went up. And in Southeast Australia, the corrections are pretty small. But if you go offshore and in remote areas of Central Australia, there's quite large corrections. And the reason for that is this. This is the Australian National Seismic Network as it looks like today. In Southeast Australia, combined with other networks, we've got pretty good coverage. But in Central Australia, most of the stations are a long way from the earthquake, and therefore the magnitude you infer is very sensitive to your choice of attenuation. And also earthquakes offshore are wet and there's no seismic stations. Hence we needed bigger corrections there, and this is one of the reasons why, compared to the previous map, HAZ in these areas has generally gone down. It's because of the new corrections in the magnitude. To cut a long story short, here is the final earthquake catalogue. Online at the moment we have 21,000 earthquakes. Offline we have now 36,000 by combining all these different catalogues from these different networks, and I'm showing everything we've got here from any magnitude. And generally speaking, earthquakes are not evenly distributed across Australia. Traditionally there's 4 seismic zones. Northwest Shelf seismic zone, which is offshore. Southwest seismic zone, which includes the Meckering earthquake. Mount Lofty and Flinders Ranger zone, I'm going to talk a lot about that over the next hour or so, which is in Central Australia, and where we're standing right now, the Southeast Australia seismic zone. And you can see there's a range of earthquakes, but we see more small ones where we've got better network and better coverage than we see offshore, for example. Again, that's due to coverage, essentially. So we've got a better, we think, catalogue, which is more complete and hopefully has a more consistent set of magnitudes than any catalogue to date. Now, we use the past in order to predict the future, and that involves statistics. It's pretty hard to avoid statistics when you talk about this course, but when you talk about this topic, we'll have a go about looking a little bit about statistics. Now, we're going to calculate the hazard at the end of this talk with a program called EQRM, the Geoscience Australia's Earthquake Risk Model. It calculates the hazard by essentially assuming that earthquakes are uniformly distributed across something called a seismic zone and are equally likely through time. So one question is, how well does this represent the seismicity in Australia? So this is a simple plot. It shows the number of earthquakes per annum across Australia from 1840 to 2010. And the sporadic seismicity between 1880 and 1960, and earthquakes become really popular in the 60s. Now, it would be incorrect to infer from this that earthquakes are more likely since 1960. It's not due to the hippies. What has happened is that we started building seismic networks, basically, in a major way, and we started picking up a lot of these smaller earthquakes. Before that, we had only a few stations, and if you go right back to the 1840s, it's based on basically felt reports, articles in newspapers, that sort of thing. It took about 20 years for the network to be built, from 1960 to 1980, which is why that's sloping up. And even today, the new stations are being added all the time. If you look from sort of 1980 to 2010, we get somewhere between 500 and 1,000 earthquakes per annum, which is detected by some networks somewhere, about 2 a day. But there's a lot of variability. Some years there's 500, some years there's 1,000. So one question we can ask is the likelihood of an earthquake constant each year, or is there variations, which are statistically significant? And that involves some stats. So let's look at the Southwest Seismic Zone, for example. Let's look at the number of earthquakes in a 3-week period. If you look at the red curve, there's about 600 3-week periods with no earthquakes, 150 with 1, about 50 with 2. Now you can calculate, and I am not going to prove that here, that a Poissonian distribution, theoretical distribution, would be the blue curve, where you'd expect about 400 3-week periods to have no earthquakes, and so on. What this indicates is that the catalogue in this area is clustered. There are more periods than we would expect with no earthquakes, and there are more periods than we expect with lots of earthquakes. They're not randomly distributed. And the best example of that is Tennant Creek, up here in the Central Australia. Between 1960 and 1989, as far as we can tell in the earthquake catalogue, there was nothing. Zero. But in 1988, when we got these big series of 3 earthquakes, we created an aftershock sequence, which created 1,000 earthquakes. And then earthquakes has continued oscillating along ever since. This is inconsistent with the idea that earthquake probability over this sort of spatial scale is constant through time. It went up dramatically when the big earthquake happened and has stayed up to some extent ever since. So what we see in Australia is basically main shocks within trigger series of aftershocks. So we need a way of going through the catalogue and splitting out the main shocks from the aftershocks, from the clustered seismicity. So Mark Leonard, mostly, developed an automatic method for pretty much classifying earthquakes into these two types. I'm not going to go through the detail here, it's in the report. But it's basically a series of spatial and temporal filters which try to pull out the big main shock earthquakes and put everything else, all the clustered seismicity, into another catalogue of aftershocks, swarms, foreshocks, that sort of thing. Clustered earthquakes are by far the majority of earthquakes in Australia. Tennant Creek's a good example. There was either 1 or 3 main shocks and thousands of aftershocks. But the main shocks are the big ones. And we're going to look at the hazard from these two types of earthquakes separately, which is why we're splitting them. This is the distribution of the main shocks with the aftershocks removed. Red is what we observe, and blue is the theoretical distribution. The numbers are much smaller because we've taken a lot of the earthquakes out, the aftershocks, but it now appears to be random in time. So we've found earthquakes that are not increasing or decreasing in probability, but are constant to the 1960s. You can apply the same sort of analysis spatially. This is a plot looking at the spatial density of earthquakes. Again, this is produced by Mark Leonard. It goes from 0 to 30 earthquakes per cell, so for 1 degree by 1 degree cell. And even after removing the aftershocks, it's still not uniform. And it can be shown, and again this is in other papers, I won't talk about it here, that basically we have 3 random processes where we think are going on within Australia. Sort of a background rate, which covers most of Australia, but it's very low. Tennant Creek is an example of an earthquake in the background zone. Regional areas, which are medium area and medium rate, the seismic zones I mentioned earlier are an example, and local hotspots of activity, or local zones, where you get 20, 30 earthquakes, main shock earthquakes within the same area, which seem to be small area but high rate. So what does this mean for the earthquake hazard map? We had to try to get the hazard map working with EKRM. So what we tried to do is to respect that kind of statistical observation and work with what we had. So basically, to summarise it very simply, we calculate the hazard for 3 separate layers and then combine them at the end of the process. This is a bit of a non-standard way of doing earthquake hazard. So we have a background layer or background zones, which cover most of the country, regional layers, which cover the seismic zones, and local layers, which cover not only clusters of main shocks, but also aftershocks. I'll talk about how we do those later. So this is how we split the country up to look at the background rates of seismicity. We split the country up basically on gross geology, cratonic, non-cratonic and extended, shown here. And we calculate the hazard assuming that over the long term earthquakes in each of these zones spread themselves out uniformly, and this basically provides a floor or background hazard, and this is how we try to capture the hazard for things like Tennant Creek. The regional zones are based entirely on the seismic density plots. This is more of a traditional kind of hazard map. These are the source zones which were identified. We went through a fairly systematic process of identifying, but most of the northern ones are highly subjective. We don't argue with that. But basically they're reflecting the concentrations of seismicity, and where we have a minimum number of earthquakes and they don't cross geological boundaries. And there's hotspots, these zones of intense activity. And we've gone through and analysed all the areas indicated by cyan circles, or specifically Mark has. Now, let's recap. We've taken the earthquake catalogue, we've statistically analysed it to find areas where earthquakes are randomly distributed in space and time. What we need to now worry about is how big do they get. So, to understand that, you need to understand something called the Gutenberg-Richter law. And that's basically the log of the number of earthquakes above n is equal to A minus B times M, where M is the magnitude, A and B are constants. So let's look at the Gutenberg-Richter plot for the whole of Australia. This shows the number of earthquakes above the magnitude given by the x-axis. And roughly, if you look at the numbers at the top, just above the figure, we get a magnitude 5 somewhere in Australia once per year. And we get a 6.5 or greater once every 0.05 years, or in other words, roughly once every 20 years. That's straightly calculated by extrapolating this curve. When you get up to high magnitudes, this sort of relationship has problems because there isn't a statistically large enough number of events in the catalogue to estimate it. So what we normally do is use the small magnitudes and extrapolate out to the larger magnitudes. Now, if we use this for the earthquake hazard map of Australia, it would distribute earthquakes uniformly across the whole country and it would be very boring. And as I've just demonstrated before, earthquakes are not uniformly distributed across the country. So when we look at a small area like a source zone, we still see a straight line, still Gutenberg Richter, but we lose the higher magnitudes because basically there isn't enough events in the small areas to estimate it observationally. Now those are examples where the Gutenberg Richter curve is reasonably well constrained. If you go up to central Queensland, we have all sorts of horrible problems, and I've shown an example here. At high magnitudes, because there isn't a statistically large number of events, you get a lot of noise. You also get problems with magnitudes, as I mentioned before, which may or may not be corrected. This was before we did the correction. At low mag problems, we start missing earthquakes systematically. So, as I said, the number of earthquakes we miss is a function of the density of the network. So we might get 100% of the 3.5, 70% of the 3.2s, and 50% of the 3s, which causes the curve to bend over. Now, there are three main ways of fitting a curve to this data: maximum least MLE, maximum likelihood, least squares, and others. And they're indicated by the black, the red, and the green curve on that figure. And they give you very different results where you get a lot of these problems, such as central Queensland. So what Mark developed was basically an algorithm which goes through the three major methods for fitting curves to this data and selects the best one. This basically turns what used to be a very manual process where an analyst had to go through and specifically analyse each zone, and turns it into an automatic process. And this allows us to do sort of national scale assessments very quickly. However, going back to this figure, you can see that there's no observational data which we can use to infer the rate of large earthquakes, your 5s, your 6s, your 7s. We don't know how far to extrapolate this. This could be extrapolated out to magnitude 10. And to work out how big we need to extrapolate it, we need to use something called paleoseismology. This is the earthquake I talked about before, 1968 magnitude 6.7 Meckering earthquake. Created this huge fault scarp across the landscape, 40 kilometres long, 2 metres or more than 2 metres high. And it was a very obvious feature in the photographs. So one obvious thing is to look at the high resolution digital elevation data to see if we can see evidence of paleo earthquakes recorded permanently in the landscape. This is an example of the Burnside fault near Adelaide, where there is a feature in the DEM which looks like an offset. If we go out and investigate to prove that it's actually an earthquake, we dig a big trench through it. This work's usually done by Dan Clark and Andrew McPherson. And what you see here is two layers. There's basically dark brown layer here, dark brown layer there, and what we infer is that there's a fault comes up through here and is actually ruptured and actually displaced these two layers. By dating when the materials were buried, we can get an estimate of when this event happened, and therefore we can determine whether that fault is currently active under the current stress field. And we've done that all over Australia: South Australia, Western Australia, Eastern Australia. Dan Clark's been working on this for about 10 years. Currently he has 300 or so what we call near-point features in the database, indicated by the red lines on this particular figure. And he's classified them into different domains according to their fault length, how much offset they've had, their spatial distribution, density, and the geology and crustal terrains. This work has been presented here before, so I won't talk about it too much. But what we're going to use initially in the earthquake hazard is the fault length, the length of the actual feature we see either in the DEM or we see in the field. So let's look at domain 1, which is all the blue areas, and let's do some statistical analysis. This plot shows the number of features n on the y-axis as a function of their length. So in domain 1 we see about 60 features which are 20 kilometres or longer, going down to about 5 features which are 60 kilometres or longer, and a couple of features which are 80 to 90. Now it can be shown that if the distribution obeyed the tapered Gutenberg Richter with an maximum magnitude of 7.3, we would expect the green dashed line, which actually fits the data remarkably well. There is a couple of sections, those two very long features, and if we remove them from the catalogue, you get the red dots, which is an even better fit to that particular theoretical model. That's domain 1. If we look at domain 2, which is the Flinders and Mount Lofties over here, it's not quite so simple. What we appear to be getting here is two distributions of earthquakes. Single event features generated by one earthquake, plus very long features, which we actually think are probably multiple ruptures, nose to tail, when we can't differentiate them in the DEMs. So we went through a couple of different ways of trying to, again, separate this catalogue out into single event features and multiple event features. And what we get with various different methods is the red dots. And in domain 2, it looks like we can say reasonably well that there's earthquakes up to 7.5 seem to have occurred, and there are larger features which probably host multiple 7.5s. Again, if you want to know how we split the two catalogues, I refer you to the GA record. And generally speaking, the picture we get is this. In Eastern Australia, we get longer features, generally, as an average, 7.7. Same with extended regions, and cratonic areas, they're generally shorter and sharper. Now, this is a significant change from how maximum magnitude was developed, say, 20 years ago. How you used to do it was you looked at the earthquake catalogue and you added 1 to the maximum observed earthquake. In some parts of Australia, the maximum observed earthquake would be 4, so the Mmax would be 5 if you use that particular method. We feel now that from the work that we've done collecting near-time features, we can rule out the possibility that earthquakes anywhere are limited to 5. We think they're at least 7.25, 7.65, and potentially larger across the whole of Australia. And that has a significant impact on hazard for critical infrastructure, longer return periods, as I'll show later. And I think this is one of the major additions to the new map, is taking the paleo sort of work into calculating both the source zones and the maximum magnitude. That's length. Let's look at the physical expression of the fault scarps on the surface. Believe it or not, there are 3 fault scarps in these pictures. You would be struggling to see some of them, unless you're Dan Clark. Probably the easiest one to see is a ridge on the top right-hand corner. It's a few metres high. It's a bit easier to see on DEMs. You can see this feature going through here, and another feature going through there, which is about a 6 metre offset. But you need a high resolution DEM to see them. They're not obvious necessarily. Compare and contrast to the features we see east of Adelaide in the Mount Flinders and Lofties. You can see these features from space, in fact. This is a high-resolution DEM model, and we think most of these features here have produced big earthquakes within the last million years, or even more frequently, including the parafault which runs underneath Adelaide. So this looks like a classic example of a fault-bounded mountain range. If you look at them from the ground, they're not hard to spot. There's 300 metres high, 200 metres high. The faults which bound these scarps seem to be active in the current stress field. This is quite a different kind of behaviour than we see in Western Australia, where fault scarps are hard to find. This is the near-tonic faulting record compared to earthquakes. Earthquakes are in grayscale. The near-tonic fault features, which vary in confidence from very likely to possible, are indicated by the green dots. And if you look, say, in the southwest seismic zone, we've got plenty of green dots under the earthquakes, but they keep going and going and going right across the craton. There's no particular concentration where there's a particular concentration of earthquakes. Compared to Flinders seismic zone, where there's a good concentration of features and earthquakes, and the same in southeast Australia, where there's a reasonable concentration. Now, we don't have many features in the north. That's probably a sampling bias rather than an absence. So that's an absence of evidence, not evidence of absence. But generally speaking, in the southern part of Australia, we get a much better correlation with historic seismicity in the west. This is another piece of work I did 5 years ago now. And basically, I took the current rate of earthquakes and I tried to work out how much uplift they would generate if they had been going at the current rate for 10 million years. So this is called the uplift rate that you would infer from seismicity. And usually it varies across Australia from 50 to 200 metres of uplift. That would be produced by erosion if you compare that topography. So in the Flinders Mount Lofties, you're looking at potentially 100 metres. So possibly as much as half or a third of the relief we see there may have been generated in the last 10 million years if the current rate of earthquakes has continued over that time at the current rate. And there's a nice correlation with topography. To some extent also the same in southeast Australia, with a good correlation with topography. Not so in Western Australia, where we see very concentrated zones of seismicity which is not being reflected in the topography. There's no strain localisation here. Instead, it's pretty flat and the whole area is raised, if you like. The high rates in the northwest were before we did the magnitude corrections, but even so, they're still localised in particular areas which don't really correlate very well with topography. This suggests that they haven't been going at the current rate over geological periods of time. As Chris mentioned, we're trying to also test this geodetically in collaboration with the National Geodesy Program. We've been putting instruments out in those 3 circles and in Victoria. We don't know exactly what we're going to find until we actually have processed the data, but we suspect that the geodetic rates in the southwest corner of Australia will be much lower than the seismic rates, but probably correspond better. In that case, what's really going on in the southwest seismic? And there's more energy coming out than is being put in tectonically. So why do we get this difference? One theory that's been often promoted is high heat flow, but there are areas in Australia with high heat flow which don't produce lots of earthquakes. The theory we had in the Braun paper was this fundamentally due to fundamental differences in lithospheric thickness. So this is the thickness of cold rocks, if you like, which is thicker in the west than the east. And what we think might be happening is the whole of the lithosphere in the west is contracting, and inheritance structures all over the place are just popping off fairly randomly, but there's no particular concentration of features, concentration of activity in the long term in particular areas. So seismicity moves around if you look at it over geological timescales. In the east, the lithosphere is thinner and things are being concentrated into particular areas. Another idea which John Corley Long mentioned to me a couple of weeks ago, there's actually a transform coming from the spreading ridge to the south here, which comes up and connects to the Tasman line. So possibly stresses from the plate margin are being concentrated into particular areas due to very large-scale plate forces. I thought I'd mention that as another possibility. So it's probably a combination of differences in physical properties of the different parts of Australia plus different concentrations of stress, which is causing this. That's all fascinating, but what does it mean for a hazard map? We're interested in the future, not the past. What we suspect now, based on what we currently know, is that we expect the Flinders Mount Lofties in southeast Australia to continue at their current rates probably for millions of years into the future. They seem to be going for millions of years thus far. In the south seismic zone and other areas of the craton, we expect the locus of activity to actually move around over geological timescales, probably hundreds to thousands of years. That would explain a generalised uplift with no concentration in any particular area. And the third one is hotspots, which seem to start suddenly and we think probably fade over even shorter timescales. However, some of them seem to last quite a long time. Tennant Creek again. Again, zero earthquakes, big foreshocks, but continued activity which lasts for decades. What we think is going on here is that we basically have a piece of crust, it's being compressed in some way, it doesn't necessarily produce earthquakes, it stores all that energy elastically. There's a big shock, in this case 3 big earthquakes. Produces a whole bunch of swarms of aftershocks, but it can take decades for the crust to return back to normal. And in that period, there's elevated but continued activity. So we're often asked why we don't ignore Tennant Creek, and if it was just zero earthquakes, foreshocks, aftershocks, and then nothing, we probably would. But since this continued activity lasts for decades, it's probably going to last for a significant proportion of the next 50 years, in other words, for the lifespan of the building. And we would argue that you have to take that into account should you wish to build an apartment block 80 kilometres to the southwest of Tennant Creek for some peculiar reason. You probably have other problems if you're doing that, but anyway. So what we do for calculating the hazard at the local scale is we only use recent earthquakes in the last 20 years, which in the case of Tennant Creek would cut out most of the aftershocks. That's how we calculate the rate. It's purely based on the rates of continued activity since the big earthquake and foreshock sequence. We also usually use a smaller Mmax, basically because the idea is when you have a big earthquake, it only affects the immediate neighbourhood of the earthquake, and therefore only loads a relatively small part. That's still very uncertain, it's a guess, but it seems to be consistent with what we've seen. So now we've worked out how earthquakes are spatially distributed, some idea. We've tried to work out how likely certain size earthquakes are. We need to work out how big they shake, how much they shake the ground. Now, ground motion attenuation is basically the change in the intensity of ground shaking as seismic waves propagate from an earthquake rupture. Usually decrease in intensity with increasing distance, as I said, and also it depends on the frequency of ground motion. High frequency waves decay faster. Also, larger magnitude earthquakes generate more low frequency energy. And to calculate that, you use a big scary equation. Here is a big scary equation. It's the amplitude is a function of the moment, which is the magnitude, the distance, and the frequency equals a whole bunch of different stuff. It's actually quite complicated to work out the amplitude of ground motion at a particular distance, which is why we gave the job to Trevor Allen. What he does is he tries to use existing earthquakes to estimate what we call the earthquake ground motion constants, Q, the stress drop, that sort of thing. Then we randomly select a set of those parameters within their uncertainty bounds, plus or minus 1 sigma. We use a program called XSIM to then solve that equation, and then we repeat step 2. The reason we don't just do this once is because we know that within a particular area these physical properties of the Earth vary, so we want to get an idea of not only what the mean is, but how much it varies around that mean. We then fit a curve through the resulting data set. So here's an example from Southeast Australia. So what he did was he looked at all these earthquakes in Southeast Australia and a few from Queensland, looked at what the ground motion, observed ground motion waveforms were at the white triangles, which are the stations, and then tried to infer a bunch of cues, stress drops and that sort of thing. For each possible combination, he simulated what the ground motion would be theoretically, which is all the little grey dots. And that's on a log scale, so it's a log of the response spectral acceleration on the y-axis versus the log of the distance on the x-axis. And basically ground motion decays logarithmically as you go away from the earthquake source. And there's about an order of magnitude uncertainty in what particular ground motion you would get due to the uncertainty in ground motion prediction parameters. But there's a mean through the middle with a variance you can pick. And we use that in the earthquake hazard map. Now, one of the big questions is how well does this work in practice? So after he did most of this work, we had the Murray earthquake, which is a big earthquake to the east of Melbourne, picked up on a lot of stations. Black is what we observed. And lo and behold, Trevor's model, right to the middle, both at that station and that station, which was a relief to all of us. However, we also plot other ground motion equations that have been used, and often the ones we get overseas are much higher ground motions, like Toro 1997, which is mid-continent, some of the really early ones from Gall, Chu and Young's. We seem to actually get less ground motion at the same distance than a lot of other places, which does suggest that ground motion is indeed different in Australia, and we need Australian-specific ground motion prediction equations. We repeated that kind of analysis for 100 earthquakes, mostly from Southeast Australia and a few from the Southwest Seismic Zone, and compared how well we did over a range of different frequencies. We then had a workshop with a range of different experts from Australia, who then picked the top 3 models for each particular zone, and then the final hazard map was a weighted sum of the 3 models shown here, which I won't really talk about. But basically we've got Trevor's model, Southeast Australian, which is the bottom one, 2 by Paul Somerville, which we originally contracted him to do, which use a completely different method, and a couple of international models just to give us some variance, basically, just in case parts of Australia are more like Eastern North America or California global. Hazard maps. This is how EQM actually uses all that information. So what we do is we distribute a synthetic catalogue of earthquakes around one particular source zone randomly. We know we can do that because we've analysed the statistics of the earthquakes to work out what part of Australia this can be done for. We give each earthquake a random magnitude and event probability based on the Gutenberg-Richter relationship. I've explained how we've done that. We calculate the ground motion to a set of points using one of those models. I've explained how we did that. And then we actually work out the probabilistic hazard. It's basically worked out by summing the probability of all events that exceed a particular ground motion at a site. The synthetic catalogue is typically around 22 million or more earthquakes. So this is a fairly computationally intensive task. As I said, we can calculate a whole variety of different maps. So the one on the left shows the ground motion expressed as G, which has 1 chance in 500 of being exceeded in different parts of Australia, ignoring hotspots. So if you really don't like hotspots, that's the map for you. If you really love hotspots, the map on the right is for you, because that just has the hazard from the hotspots. And it is much higher, but very localised in particular areas. Now, we use G because that's what's in the building code, but most people aren't really that familiar with what it really means. So this is the earthquake hazard map combining all 3 layers in a way which you can see the report to see how exactly we did that. And I'm using the Allen equation to work out what this actually means for a design earthquake. So let's suppose you're building something here in the middle of Australia for some peculiar reason. There. Hazard says it's 0.02. G has a 10% probability of being exceeded every 50 years. That's about equivalent to a magnitude 5.5 and 40 kilometres. That's essentially what you're designing for. If you get a 5.5 closer than that, your building may experience ground motion which exceeds what it's designed for. If you look at the darker blue regions, 0.04 G, what you're designing for is a closer earthquake of the same magnitude, a magnitude 5.5 at 25. Yellow, it's 5.5 at 20. Orange, it's 5.5 at 17. In the red areas, you're looking at a fairly close earthquake, magnitude 5.5 at 14. In all cases, this is less than the ground motion you'd expect from a 5.5 at 5 Ks. So this illustrates an important point of what earthquake hazard maps and building codes are about. They're not about making your house earthquake proof. What they are about is trying to make sure that distant or small earthquakes don't damage your building. But if you get an earthquake close in, then your building will experience ground motions exceeding what it's designed for, and therefore it may experience damage. So even if this was implemented in the building code and all buildings in Australia fitted it, you still need to have an earthquake alert service, and you still need to prepare for earthquakes. Emergency managers will not go out of business. But what they should be only concerned with is close, big earthquakes. If you design everything with a 10% probability of being seeded, which is typically what you use for, say, an apartment block. For more important buildings, you might want to design for the bedrock ground motion with a 1% probability of being exceeded every 50 years. That's a larger ground motion. And effectively what you're designed for there is an earthquake closer in or a bigger earthquake at the same distance. So you see there's not just one earthquake hazard map. There's an earthquake hazard map for every type of building you can imagine, depending on how important you think it is. Apartment blocks might have a relatively use a low hazard map, low return period hazard map. More important buildings use a longer return period hazard map. Now, what they do in the building code is they don't have a different hazard map for each type of building importance. Instead, they take the 500-year hazard map and multiply it by the probability factor, KP factor, to look at what the ground motion would be at a longer return period. So what we're going from here is less important buildings to more important buildings. The orange curve here is what's currently in the building code, things like that. Now we've actually calculated the hazard at a range of different return periods for all these cities, Adelaide, Canberra, Brisbane. The rates vary, but everywhere in Australia it's increasing faster with a return period than what's currently in the building code. And this, I would argue, is one of the more significant findings from our work. We would argue that the increase in ground motion you need to design for more important buildings should be more than what is currently in the building code. At 500 years, the difference between this map and the old map is of the order of a few hundredths of a G, which is like shifting your design earthquake 5Ks, 10Ks forward and back. But it's probably the effect at longer return periods that may actually be the more significant one. Basically, we don't think long return period, the more important buildings necessarily are being designed for as much shaking as they should be. As we can calculate the hazard, calculate the ground motion numerically, we can also calculate it for different frequencies of ground motion. And different buildings resonate at different frequencies. So short buildings might resonate at short frequencies, a tall building at tall frequencies. So not only can we calculate the hazard for different levels of importance, we can calculate the hazard for different heights of building, from short to tall. Again, in the building code they use multipliers for this, but on Bedrock we can actually now calculate it. So we haven't actually just produced one hazard map. We've done one hazard assessment, but it can be plotted for a range of different building types, more or less important, short and tall. And we can calculate numerically the hazard for all of them. So what happened last year? At the end of last year, we released one version of the 500-year map, simplified, onto the web. This was thanks to the Darwin tool as an experiment. Some neat features. You can actually work out what the hazard is by hovering your mouse over a particular area. You can change the transparency of the map, and you can also overlay it with some other data sets, geology, land cover, gravity image, and magnetic. And if you're interested in how earthquake hazard corresponds to those, I recommend that you do that. It's quite interesting. You also download the PDF, which looks like this. So what we produced was a GA record, several hundred pages, 140 pages, which detailed in great detail how we put all the map together. So it's a technical document, but we wanted to put that on the web and make it externally available for others to use. And this was internationally peer reviewed. And we're also in the process now of putting together an actual paper into a journal as well. Since the launch, we've received various inquiries. Now this is basically telling us what we haven't produced. We've had quite a few engineers who are designing critical infrastructure, things like dams, who want much longer return periods, 10,000 years, or the maximum credible earthquake. And some designers are also after hazard curves. They obviously know a lot about their building and know how it resonates. So as a result of these inquiries, what we're putting together now is an additional GA record, or will soon anyway, which covers a range of different return periods and a range of different spectral periods to basically give us a record we can provide to these people rather than just attaching things to emails. In terms of inquiries from the States, it's been enormously concentrated by inquiries from Victoria. I suspect they've been sensitised by the Murray earthquake, unlike the other jurisdictions. So we've had requests from VicPol for the GIS version of this. I've presented to the Vic SES Regional Managers Forum. We've been invited to participate in an earthquake exercise in Murray, or in the Latrobe Valley as well. And we've had multiple inquiries from the risk modelers, people who actually do this for a living, usually from insurance companies. Some want the map, other want the catalogue, other want the zones. It's very specific depending on whether they do hazard in-house or external. So to answer the first few questions, we'll be producing more products and potentially another layer to the tool, hopefully in the next few months. So in summary, we've gone from one map without any particular details about how it's put together to a range of different maps covering all sorts of different buildings, from more important to less important, from tall to short. We've completely updated the earthquake catalogue, added another 15,000 events to what's in the online catalogue. We revised pretty much, very simply anyway, but pretty much every magnitude in there to get a more consistent magnitude scale for all the earthquakes. More could be done in that area to improve the consistency, but it's a step forward, I think. We've developed automatic methods for declustering the catalogue and estimating A and B values. This should make future hazard maps much quicker and easier to do. We've started to encourage some of the results from paleoseismology for the very first time into an earthquake hazard map, including MMAX and how we design the zones. We've included some strain-specific ground motion equations, and more importantly, we've published all of this onto the web into a technical document. So we can stand and fall by our predictions, basically. We have said that the MMAX in this area will be X. We've said that the ground motion will be Y. We've said that the rate will be Z. Over the next few years, we'll see how well we did, whether we get a bigger earthquake than we expect, whether the ground motions are different than what we expect, whether the rates are higher or lower. And we can use that to develop the map progressively and hopefully get better and better forecasts over time. This is all bedrock hazard. We can also use this to calculate the hazard, including surface conditions, and use that to estimate risk, which is the likelihood of damage in different parts of Australia. And that will be a useful product mostly for emergency managers, but also for us, because if we understand which area is most likely to be exposed to, most likely to experience damage, we can use that to guide where we do further research and where we can improve our hazard and risk estimates. So thank you very much. If you're the guy on the left, we'll fix it in the next map. If you're the middle guy, I'm sorry, but this is a statistical talk. And if you're the guy on the right, please fire away.